Hi everyone, welcome back to the AI language. So today we are going to do something pretty amazing. We're going to connect three agents which are shown over here in the red, green and blue terminal windows together with A2A, and we're also going to connect our host agent, which is this red agent over here, with an MCP server. So you'll have A2A connecting all the three agents and MCP connecting one of the agents with a server to utilize all the tools on that server together. All this is going to happen in the same setup, and the host agent is the agent that will decide whether it wants to use the other agents to fulfill a task or whether it wants to use the MCP server and its tools to fulfill a task. So this is our first attempt to basically make a single unified system with agents running and using A2A and MCP at the same time. Before I begin, I would request you to please subscribe to my channel, The AI Language, on YouTube. By subscribing to the channel, you get access to the code base for A2A and for MCP and get notified about all the videos I release around A2A and MCP as well. Alright, so now let's do the ultimate demo of the A2A and MCP system combined. So I'm going to start the tell time agent over here, which is going to basically tell us the time to generate a poetic greeting. This is the greeting agent in green. So I'm going to start this greeting agent over here, and this is going to generate a poetic greeting based on the current time of day. This is our host agent or orchestrator. So I'm going to start it in the red terminal window over here, and this is going to orchestrate all the communication. And over here I'm going to start my client. Now let's ask the client to do this. Alright, so I'm going to ask it to generate a greeting for me using the other agents and then write the greeting by running a terminal command to a file called A2A MCP greeting.txt using the run command tool. Let's press enter. Alright, so host agent fires up. It fires up the greeting agent as well. This basically hits the tell time agent. Alright, so now we get the response that agent says, okay, I have generated the greeting and written it to the file A2A MCP greeting.txt. So let's go to the Finder window now. Okay, so we have this file over here. Let's open this. So it says, good afternoon, the clock strikes nearly 5. A gentle breeze whispers secrets of the day. May this time bring peace and joy your way. So that's the poetic greeting that we have got. Alright, and you can see that this is the greeting that the greeting agent had produced. Good afternoon, the clock strikes nearly 5. A gentle breeze whispers secrets of the day, and may this time bring peace and joy your way. So I hope you realize that what's happening over here is pretty amazing and exciting. So you have an A2A client which is basically exposed through this command line app where we can write a query. This is connected to a host agent which can actually discover two more agents. One is the greeting agent and one is the tell time agent. It can also discover a tool called the run command tool, which is available on an MCP server. And now you can just give it one single query, which basically entails the use of the other two agents. So it decides to use the greeting agent. The greeting agent itself decides to use the tell time agent and sends back a greeting. And then the host agent actually hits our MCP server to run the tool to create a file, which we just saw in the terminal. So this is a unified MCP and A2A system that's working together to do all this stuff with just one simple query. And this is like a base which you can actually use to expand this into as complex a system as you want. But we have successfully done this today, that we've actually run A2A and MCP in a single system with a single host agent. Alright, so before we jump into the setup and the running of this agent and going through the code, let me go through the architecture and do a quick recap of how all this works. So A2A with multiple agents and MCP works based on three different layers. So first is the front end. And this is basically your app where your user types in the query. For now, we are using a command line interface or a command line app. This app basically uses an A2A client to connect through the A2A protocol to the second layer, and this is the multi-agent system that we have built that works with A2A and MCP both, right? And then this multi-agent system can now connect to remote A2A agents and MCP servers, and these are the agents and servers that somebody else might have made or some other organizations might have provided to you, or they might be your own MCP servers and A2A agents. And the idea is that your agent is versatile enough to connect through MCP and A2A to any of these agents or servers. Now, once your query is received by the app frontend, it passes it to a host agent. The host agent receives that query on its A2A server, and then it passes on this query to the orchestrator. The orchestrator is provided two tools, the list agents tool and the delegate task tool. The list agents tool helps the orchestrator discover all the agents through an agent registry, which is where we put the URLs for all the different agents that we want our system to work with. The delegate task tool helps the host agent delegate a certain task to one of the remote agents. It basically uses an agent connector that spins up an A2A client, and then it uses A2A protocol to pass on that task to the remote agent. The remote agent receives that task on its A2A server and then completes the task and returns the response. The remote agent itself might have an orchestrator that can use either the same registry or some other registry to connect with other agents. So this is the entire A2A branch which is shown in red. The orchestrator is also provided with an MCP connector. So the MCP connector basically lists all the servers in your MCP config.json. Then it basically spins up MCP clients which use the model context protocol or MCP to connect to all the servers that are listed in this config.json file. Now each server might have multiple tools. So ultimately you have a set of tools that basically are discovered over here through this process. All these tools are then returned back to the orchestrator, and apart from these two tools, it has access to those individual tools as well, which it can then call as MCP tools through the model context protocol. So the orchestrator then basically has all these tools, the list agents tool and the delegate task tool, to basically take in the query from the user and then fulfill it. Once all the responses from the tools and the remote agents are returned, the orchestrator stitches them together and returns a final response to your user through the A2A protocol on the app frontend. Alright, so now let's look at how to get the code and set it up and then finally run it on your system. So first, please check out the code using the link that I've provided in the description. Once you check it out, you'll basically see an A2A_samples folder, and you'll have multiple code versions over here that we have covered in different videos. The one that we're discussing right now is version 4 Multi-Agent MCP. And what you can do is you can actually separately open this particular folder. So I'm going to do that now. Alright, so I have basically opened the version 4 Multi-Agent MCP folder inside my VS Code. And once you do that, you're going to see a folder structure like this. So you're going to see all the agents over here. So you have a greeting agent, you have a host agent, and you have a tell time agent. You also have an app over here, which is the command line app that we are using. You then have the A2A client inside the client.py folder. You have different data models. You have a server folder with the A2A server code and the task manager over here. And finally, you have utilities. So for the utilities, we basically have two folders. Since this code combines both A2A and MCP, the A2A related utilities are mentioned inside the A2A folder. So you have a agent connect.py file, which basically is the agent connector. You have the agent discovery mechanism, and you have the agent registry, which basically contains all the agents that we want to connect to. Similarly, you have an MCP folder over here. So for MCP, you have an MCP config.json. We're using the word config because MCP uses the word config, whereas A2A uses agent registry. But these are essentially files that tell what all different MCP servers and A2A agents are available. So we have the MCP config, which basically tells us about the one server that we have for now. We have the MCP connect file, which is the MCP connector that connects with the MCP server, and we have the discovery mechanism with MCP discovery. When you check out this code, you'll also get a pyproject.toml file, which has all the dependencies that you'll need to run this code. And now we are going to see how to run this code. To set up the code, shift to the version 4 folder that you just checked out. So we have checked out the A2A samples folder. I store it in a parent folder, which is just called A2A, and then the version 4 multi-agent MCP folder is inside the A2A samples. Let's change to this directory. When you check out this folder, you will not have a virtual environment. So I've deleted mine, and now we just type in this command, uv sync all groups. When you do this, It is basically going to create the virtual environment folder for you and install all the dependencies that are listed in the py project toml file. Now let's list all the files over here, and you can see that we have the .venv folder over here. Let's activate this virtual environment, and now we have the virtual environment version 4 multi-agent MCP activated. So this is all that you need for the setup. Please note that we are also using UV over here, which is a fast package manager for Python. And of course we have Python and VS Code installed. So I'm not covering those steps over here. We have covered those in previous videos. And if you'd like, you can look at those videos, or you can actually go and search online. It's a pretty simple thing to set up UV, VS Code and Python on your computer. Alright, so finally now let's look at our config.json file for MCP and the agent registry and the environment variables file. Alright, so you can see that we have the utilities folder with A2A and MCP folders. The A2A folder has an agent registry.json file. So this is where we basically put all the information about our A2A agents. We have a MCP config.json file inside the MCP folder where we put our MCP server configuration, and we have a .env file in the version 4 multi-agent folder directly, which is going to basically have our Google's API key. So let's first go through MCP config.json file. So this file has the config for our MCP servers. We're just using one server over here. You can actually use any server that you want. I am using the terminal server as a demo server over here. And again, please look at the video where we designed and built this terminal MCP server if you wish to use this. Again, I'm going to specify the information about that video in the description. Next, we have the agent registry.json. So if you have watched our previous video where we did not have MCP integrated, you'll know that we basically specify the A2A server base URLs over here, which is going to then be read by our agent discovery process and then be connected by the A2A clients. Finally, we have the .env file, and over here you need to put the Google API key. Now when you're going to check out the code, we don't get this file because this is a private key which we don't want to push to GitHub or any other such repository. So now I'll tell you how to create this file and how to get the Google API key for free. You can actually go to aistudio.google.com and log in through your Gmail account, and they're going to give you a Gemini API key for free. So there are some terms and conditions that you can check when you take this key, and essentially you can actually use it for free for testing purposes with certain lower limits, and by allowing them to use your data while training their model. And this then makes it an ideal choice for this tutorial and experimentation. So I'm on aistudio.google.com, and when I visit this site, it automatically gives me a prompt to get an API key over here. And otherwise, I think there's a button over here also to get the API key. So I'm just going to click on get API key over here. Okay, so there's a code to test the Gemini API, and there's a create API key button over here. So let me just use the API key from here. It's going to now generate the API key for me. And you should use your API keys securely and not share them or embed them in code that the public can view. I'm going to disable this after the tutorial. For now, I'm just going to copy it from here and let it be visible. So again, let's go back to the terminal and go to the folder where we have checked out the code for the version 4 A2A agents. Alright, so we changed the directory to A2A samples version 4 multi-agent MCP. Now once you're in this folder, type touch.env, and this is going to create the .env file. Now once you have the key from Google AI Studio, please paste the key over here as shown and then save this .env file. And once you have saved it, your code will be basically able to load this environment key from the .env file and use it to communicate with Gemini's LLM. Alright, so now we are going to see how to run all the agents and how to run the command line app. So first we need to run the tell time agent. To run the tell time agent, we type uv space run space python -m, and then we basically type agents.tellTime agent, which is the path to that agent. We basically provide a host where the agent should be hosted, which is localhost, and we provided a port which is 10,000, and we press enter, and this basically starts the tell time agent for us on localhost 10,000. So I'm going to press Ctrl+C to quit and see how we can start the other agents as well. To start the greeting agent, we pretty much have the same command, but the path for the agent and the port is changed. So we have agents.greeting_agent this time, and we have the port 10,001 that we're going to use, and we press enter. And this basically starts the greeting agent for us on localhost 10,001. We now press Ctrl C to quit, and now we're going to start the third agent, which is the host agent. To start the host agent, we basically update the port to 10,002 and we provide the path, which is agents.host_agent.entry, which is the complete path for the host agent, and we press enter. Alright, so this is going to start your host agent, and you can see that the connection attempts to the other two agents have failed because we don't have them running right now. While actually running this, we'll actually run all the agents together so that the host agent can discover and connect to the other agents successfully. So now we are going to start the command line app, and now we'll start the command line app. To do that, we type uv run python -m, and then we provide the path to the app, which is app.cmd.cmd. And basically the app needs to know which agent it wants to connect to. So we provide the host agent path over here. An interesting experiment would be to actually connect this app directly with the greeting agent or the tell time agent, and you'll see that it wonderfully connects to those agents, which just points out to the modularity of the code. That same app can basically be used to connect to any kind of agent, and when you connect to a specific agent, you can actually only connect to that agent and perform the tasks that that agent helps you with, because you'll not have the host agent connected at that point in time. So we press enter, and then we get this query as to what would you want to send to the agent. So we can type quit to quit this, and this is how you start all the agents and your command line app. We've already looked at a demo at the beginning, which basically shows how these agents talk together. We can deactivate the virtual environment by typing deactivate, and this is going to deactivate our virtual environment. Let's also have a look at our MCP server. Just note that the MCP server does not need to be started as such, because the MCP client itself is going to start the server and bring it online and then query all the tools from there. But just to show you, I have checked out the MCP server using the link. Let me go to that folder. So I've checked it out in a base MCP folder, which has a subfolder called servers, where I put all my servers, and then I have a terminal server folder. This is basically what has been checked out from the GitHub link. Now, if we list all the files over here, we can see that we have the terminal server.py file, which is basically the entire logic for this server. This folder also has some other servers which you're not going to use for now. If you'd like to know more about how this terminal server works and how we built it, you can look at the previous video where we have covered this when we were learning about MCP. I have provided information about that in the description. Alright, so now let's go through the code, and what we are going to do is we're going to essentially use the same code that we have used before with some changes to the orchestrator and addition of the MCP discovery and communication logic. So I'm going to first go through the orchestrator code. So the purpose of the orchestrator agent is to discover and call the other A2A agents via the discovery client and agent connector. It also discovers and loads the MCP tools via the MCP connector, and it exposes each A2A action and each MCP tool as its own callable tool. This also defines the orchestrator task manager to serve this agent over JSON RPC. This is what basically connects the agent to the outside world to handle all the tasks that are coming in from the A2A client. Alright, so we have the imports and the loading of the environment variables over here. Then we have the Google ADK and Gemini imports, and we have seen this before, so I'll not go into a lot of details over here. Then we have the A2A infrastructure imports. So basically we have the models and we have the server code giving us the base task manager, which we basically extend to then create a task manager for the orchestrator. Then we have the utilities for the A2A agent discovery and agent connector. And now this is what is new. So we have a utility for MCP to connect to MCP, which is the MCP connector over here. We then have the agent related models, which we are importing to get the agent card model. And then we have some basic logging setup. Now we go to the orchestrator agent. So this will basically discover the A2A agents via discovery client, and basically it gets a list of agent cards. Then it connects to each A2A agent with the agent connector. It discovers the MCP servers via MCP connector and loads the MCP tools. It exposes each A2A action and each MCP tool as its own callable tool, as we read before, and then it routes the user queries by picking up and invoking the correct tool. So let's go through the initialization logic over here. So The init function basically initializes the orchestrator with the discovered A2A agents and MCP tools. So the arguments are the agent cards, which is what we are passing in from the entry code that we saw earlier. Ideally, just as we did with the greeting agent, which you might have seen in the previous video, we can actually do the list agent functionality entirely over here without passing the agent cards as well. But we're just going to continue with this because this is pretty much equivalent, more or less the same as what we are doing in the discovery client. Just the fact that discovery is not happening inside the agent code, but outside it. Then we build connectors for each A2A agent. So this is what we have seen earlier as well. Now what is new is loading all the MCP tools. So we basically define an MCP connector and we get all the MCP tools. So we're going to look at the MCP connector after this, but let's just for now realize that we're getting a list of MCP tools over here. Now all these are basically MCP tools which have an MCP tool.run function. And what we need to do is we need to wrap each of these MCP tool.run into a simple async function that we can pass to the agent development kit, ADK's LLM agent. So what we do is we define an empty list of wrappers in number 3 over here, and then we basically make the wrapper for the tool. So this is a function where we pass an MCP tool and it will basically return a wrapper for that. So what we're doing over here is that basically we are defining an async function that accepts a single dictionary of arguments. Given a tool, it basically returns tool.run with the arguments, and this is what the wrapper is. We assign the wrapper the name which is the same as the tool name. So essentially now you can run the MCP tool by running the wrapper which has the same name, and running the wrapper essentially invokes the tool by using tool.run arguments, and arguments are what is basically provided to the wrapper as a dictionary. Now we actually do the execution for this particular function. So we iterate through all the tools. We make the wrapper for that tool, then we append it to our wrappers list, and we basically register a function tool object for each of these wrappers. This is what basically is expected by Gemini, and then we basically log that we have wrapped the MCP tool for the LLM with this particular name. Now we can go to the next step, which will simply build the Gemini LLM agent and its runner. So we have basically self.build agent, which is going to build the agent. We provide a user ID and a runner object, which we have seen before. And this is going to basically help us build the agent and the runner. Now we'll look at the detail of the build agent function. So this is just simply going to create a single list of tools now. Initially, we only had the list agents and we had the delegate task tool, but now we unpack the MCP wrappers as a list of tool wrappers, and now we provided to the list of all the tools that are available for the agent, and now we have a valid list of tools which includes both the A2A aspects and also the MCP tools. Now we can return an LLM agent with all the tools similar to what we did before. One change that I have made from last time is to actually update the model to a better model, so which is 2.5 flash preview 0417, which is basically done because the 1.5 flash is a much older model and it might not be able to handle complex queries where we want to invoke A2A agents and MCP tools in just one single query. But 2.5 flash handles that pretty well, and since this is the flash version, on our free API key, it gives us 10 requests per minute as of now, and that is sufficient to test out this code. Alright, and then we have other functions like root instructions where we actually now provide an instruction around MCP tools. So you can simply go through them. These are not very difficult, and this is pretty much the same as before with some additions for MCP. We also have the list agents function and the delegate task function that we were using from before. And we have the invoke function, which basically runs the runner and invokes the tool similar to what we had before. We then have the orchestrator task manager, and you can actually go through this remaining part of the code, which I am skipping for now. It has extensive comments for you to understand, and it is pretty much the same as what we have done in our previous video. Alright, so now let's go on to the main addition in this code, which is the MCP connector. So we had loaded all the MCP tools at startup using the MCP connector and using the get tools function. So let's look at these two. So you can find the MCP connector in mcp_connect.py file, And let's start from the top over here. So the purpose is to connect each MCP server defined in MCP config.json, one FML session to list available tools, and provide an easy interface to call those tools on demand. So we have some basic imports over here, and then we import the MCP core classes for stdio communication and session handling over here. Then we have the utilities for MCP discovery. Then we load the environment variables like the API keys into our environment, and we have some basic logging. Now we have the MCP tool class. This wraps a single MCP exposed tool so we can call it easily, and it takes in the name, which is the identifier for the tool, example run command. We have the description string, which is a human readable description of the tool, and then we have the input schema. So this is the JSON schema defining the tool's expected arguments. And finally, we have the stdio server params, which are the command/arguments to start the MCP server. So in the constructor, we basically store the name of the tool and the description for later reference. We save the JSON schema to validate the arguments passed to run, and we prepare the stdio connection params so we can spawn the server on each call of this particular tool. Then we have MCP tool.run. So this basically helps us invoke the tool by spawning the MCP server via stdio, initializing an empty MCP client session, calling the name tool with provided arguments, and closing the session automatically on exit. And it returns the content from the tool's response or the raw response if there is no content. So we create an stdio connection to the MCP server. So we basically use the server parameters, and then we get the read and write streams. Now we use those read and write streams to basically create an MCP client session, and we use this variable to store that, and then we initialize the session. We call the tool that we want to call with the name and the arguments, and we get a response, and then we basically get the content out of the response and return it. Otherwise, basically we return the stringified response that we have received. Basically it contains all the description, name, input schema, etc. for the MCP tool, and a run function that it exposes so that we can invoke the tool. Now let's go to the MCP connector. So this MCP connector discovers the MCP servers from config, lists each server's tools, and caches them as MCP tool instances for easy lookup. Alright, so in the constructor, we initialize the MCP discovery to load the server definitions from JSON. So we have the MCP discovery, and we basically provided a config file that we have gotten over here. Otherwise, we use the default config, which we can see in the MCP discovery code, which is the mcp config.json file. Now we create an empty list of tools, and then we basically call load all tools to basically load tools from all the configured MCP servers immediately. The load all tool functions is basically a helper, so it runs an async routine to synchronously fetch and cache tool definitions from every MCP server. So we define the fetch function first. So what we do is we basically use the discovery client with the config file, and we do call the list servers function. And we're going to look at MCP discovery later on, but this basically gives us a list of all the servers. So it basically gets the mapping of the server name and its config dictionary. Then we iterate through each server entry, and we basically get the command. So we extract the command like python space script.py and the arguments, and we log the same over here. Then we get the params with the command and the arguments, which are the stdio server params. Now we basically open a stdio connection to the MCP server using the stdio client, and we get the read write streams, which we wrap in an MCP session over here. Then we initialize the session, and over here we basically list all the tools. We saw above when we were using the run function, we were actually using this session to call the tools. Over here we just get in the tool list, and for each tool in the tool list, we basically call self.tools.append, and we wrap that tool in an MCP tool, which is the class we had seen above. So now we have an exposed MCP tool that we can run, and we have all the information about the tool over here. Finally, we log the same on the terminal, and we handle some exceptions if they happen. And finally, we run this fetch function to load all the tools immediately. So whenever you're going to define your MCP connector class, it's basically going to run the fetch function, load all the tools, and this then will be available in your self.tools parameter, which will actually have all the MCP tools that have been loaded. Now we have the get tools function for the MCP connector that we were using earlier to get all the tools, and this basically just creates a copy of the list of MCP tool instances and returns the same. So this is your MCP connector, and now one of the main files that we just have to look at is the MCP discovery logic. This is a pretty simple logic. So this MCP discovery class is located in MCP discovery.py inside the MCP utilities folder, and it basically reads the JSON config file defining the MCP servers and provides access to the server definitions under MCP servers key, which is very common in MCP, which is what we have done in all our MCP videos before. And the config file is pretty much the standard element in all of our MCP videos. So the attributes are the config file, which is the path to the JSON file configuration. And there's a dictionary for the config, which is the parsed JSON content expected to contain MCP servers. So in the constructor, we initialize the discovery client. So we have the config file string optional. So this is basically the custom path to the MCP config JSON. If it's none, it defaults to MCP config JSON located in the same directory as this module. So we can have a look at it over here, and this is our MCP config.json file, which is already there. And now let's go back to our MCP discovery file. So we check if the config file is provided and assign that, else we just use the default file, which is mcp config.json, and we then call load config, which is going to basically parse the JSON content and hand it to the config variable over here. So the load config function attempts to open the config file in read mode. It handles some errors over here, and otherwise just simply returns the data. There's an exception handling for file not found error, and basically if parsing fails or if data is not a dictionary, there are value errors or JSON decode errors. Finally, we have the list servers function. It retrieves the mapping of server names to their configuration entries, and the JSON is expected to look like the standard config.json file format, and it returns a dictionary under MCP servers or an empty dictionary if it is missing. This is basically going to return a dictionary of server names mapping to their config data, which were located under MCP servers inside the config file. So this basically completes the new MCP utilities that we have and how we basically access them in the host agent inside the orchestrator.py file. So this, along with the previous code that we've already looked at, should complete the entire code walkthrough for this particular video. We've already looked at the demo and we've already looked at how to set this code up and how to run this. Thanks for watching. Please do like the video if you have enjoyed it. Do share it with your friends and colleagues. Please subscribe to the channel if you're not subscribed for many more A2A and MCP videos, and I'll see you in the next video.